By this point in this class, you must have realized that a lot revolves around the concept of conditioning. Conditional expectations play a central role. For this reason, it is useful to revisit this concept and view it in a more abstract manner. The basic idea is that the value of a conditional expectation is affected by a random quantity, by the value of the random variable y on which we are conditioning. It is a function of y, and therefore a random variable. Based on this observation, we will redefine the conditional expectation as a random variable and then try to understand its properties. In particular, we will develop a formula for the expected value of the conditional expectation. This will be what is known as the law of iterated expectations. After doing all this, we will follow a similar program for the conditional variance. Once more, we will see that it can be viewed as a random variable, and then we will relate its expected value with the unconditional variance. This will be the so-called law of total variance. As an illustration of the tools we are introducing in this lecture, we will consider various examples that will hopefully clarify the concepts involved. Our final and most important example will involve the sum of a random number of independent random variables. The setting here is more challenging than the case where we add a fixed number of random variables. But by using conditioning, we will be able to derive formulas for the mean and the variance.
In this segment, we revisit the concept of conditional expectation and view it as an abstract object of a special kind. To get going, let us start with something simple, the concept of a function. Let's say a function h that maps real numbers to real numbers. As a concrete instance, consider the quadratic function that maps a number x to its square. Consider now a random variable, capital X. What do we mean when we write h of x? For h defined, for example, in this particular way as the quadratic function, h of x is defined to be a random variable. Which random variable? It is the random variable that takes the value little x squared whenever capital X, the random variable, happens to take the value little x. And this is the random variable that we usually denote as the random variable x squared. Now let us come to conditional expectations. The conditional expectation of a discrete random variable is defined by this formula. It is like the ordinary expectation, except that we now live in a conditional universe in which the random variable capital Y is known to have taken a value little y. And therefore, instead of using the ordinary formula for expectations that involve the PMF of x, we now use that formula but with the conditional PMF of x, which is the appropriate PMF that applies to this conditional universe. And if it happens that the random variable capital X is continuous, we would have an alternative formula, but of the same kind, where the summation is replaced by an integral and the PMF is replaced by a PDF. Now let us look at this quantity here. We have fixed some particular little y, calculate this quantity, and what we get is a number. It is a number, but the value of that number depends on the choice of little y. If I give you a different little y, then you will get another number for this conditional expectation. This means that this quantity here is really a function of little y, and let us give a name to this function. Let us call this function g. Now that we have defined g, we can ask, what is this object? It's a function of capital Y. It's a function of a random variable, so it should be a random variable by itself. By analogy with the earlier concrete example, it is the random variable that takes the numerical value g of little y whenever capital Y happens to take the value little y. But g of little y has been defined to be the same as this conditional expectation. So it's the random variable whose value is this conditional expectation which is a particular number, if capital Y happens to take the value little y. This particular random variable that we have defined here, g of capital Y, we call it the abstract conditional expectation of the random variable x given the random variable y. To summarize, this notation here stands for a random variable. It is the random variable whose numerical value turns out to be this one if the value of the random variable capital Y happens to be little y. It is a function of capital Y. Once we know the value of capital Y, then the value of the conditional expectation is well defined, it is known, and it's equal to this particular number. It is of course a random variable, and as a random variable it has all the attributes that random variables have. For example, it has a distribution, that is a PMF or a PDF. It has a mean of its own and it has a variance of its own. So what will be next in our agenda is to talk about these attributes of this special random variable and also to use it in several examples. We have previously defined the abstract conditional expectation of one random variable given another random variable, and we discussed that it is by itself a random variable. In particular, it has an expectation or mean of its own. What is this mean? This is what we want to find out. Let us recall our development. We look at the conditional expectation of a random variable given a specific numerical value of another random variable. This is a number that depends on little y, and this can be used to define a function little g. The function little g for any particular little y tells us the numerical value of the conditional expectation. Since little g is a well-defined function, we can also now define this particular function, which is now a function of a random variable. It's a well-defined object, it's a random variable, and then we introduced this abstract notation. We define this object to be exactly this particular random variable. So now we want to calculate the expected value of this object, which is written this way. Now this notation here may look quite formidable, but let's see what is happening. Inside here we have a random variable, and we take the expected value of that random variable. Or more crisply, think of that as the expected value of g of capital Y, where g of capital Y is defined through these correspondences here. How do we calculate the expected value of a function of a random variable? Here we use the expected value rule. Assuming that y is a discrete random variable, the expected value rule takes this form. And the next step is to substitute the particular form for g of y that we have. G of y was defined in this manner, so we're dealing with the sum over all little y's of the expected value of x, given that y takes a value little y, weighted by the PMF of little y. Now, if we look at this expression, then it should look familiar. It is the expression that appears in the total expectation theorem. We take the conditional expectation under different scenarios and weigh those conditional expectations according to the probabilities of those scenarios, and this just gives us the overall expectation of the random variable x. So this step here was carried out using the total expectation theorem. So we have proved this important fact that the expectation of a conditional expectation is the same as the unconditional expectation. This important fact is called the law of iterated expectations. The proof was carried out assuming that y is discrete, so we use this particular version involving a PMF, but the proof is exactly the same for the continuous case. You would be using an integral and the PDF instead of the PMF. As the proof indicates, the law of iterated expectations is nothing but an abstract version of the total expectation theorem. It is really the total expectation theorem written in more abstract notation. But this turns out to be powerful, and also we avoid having to deal separately with discrete or continuous random variables. Here is a simple application of the law of iterated expectations. We revisit the stick breaking example, which we have seen sometime in the past. So in this example, we start with a stick that has a certain length and which we break at a point that's chosen uniformly at random throughout the length of the stick, and we call the point at which we cut the stick capital Y. So the random variable y has a uniform distribution on the interval from 0 to L and is described by this particular PDF. Then we take the piece of the stick that's left and we break it at a point that's chosen uniformly over the length of the stick that's left. So the stick that was left has a length y, and the place at which we cut it, x, is chosen uniformly over that interval. So in particular, x, or rather the conditional distribution of x given y, is uniform on that interval. So in this example, what is the expected value of x if I tell you the value of y? Well, given the value of y, the random variable x is uniform on that range, so the expected value is going to be at the midpoint and is equal to y over 2. This is an equality between numbers. For any particular number, little y, we have this equality. Now let us convert this concrete equality between numbers to a more abstract equality between random variables. This object is a random variable that takes this value whenever capital Y is little y. So this is an object that takes the value little y over 2 whenever the random variable capital Y happens to be little y. But that's the same as the random variable capital Y over 2. This is a random variable that takes this value whenever capital Y happens to be the same as little y. So the conditional expectation, the abstract conditional expectation, is a random variable because its value is determined by the random variable capital Y, and it is this particular function of the random variable capital Y. And now we can proceed and calculate the expected value of x using the law of iterated expectations. The law of iterated expectations takes this form. We have already calculated what this random variable is. It is the random variable that's equal to y over 2. So this is the same as 1/2 the expected value of y. And since y is uniform in the range from 0 to L, the expected value of y is equal to L over 2, which gives us an answer of L over 4. This is the same as the answer that we got in the past, where we actually found it using the total expectation theorem. The calculations were exactly the same as what went on here, except that here we carry out the calculation in a more abstract form. And what is important to appreciate from this example is the distinction between these two lines. This is an equality between numbers, which is true for any specific little y, whereas this is an equality between random variables. This quantity is random and this quantity is also random, meaning that their values are not known until the experiment is carried out and the specific value of capital Y is realized. This is an example, or rather a story, that's supposed to give us some insight and some intuition about what the law of iterated expectations really means. Suppose that you work for a forecasting company. And suppose that you make forecasts by calculating expected values of the quantities that you want to forecast. And of course, when you calculate an expected value, you always use whatever information you have. So here we have the beginning of the year, and you're working for a company that's trying to forecast the sales during the month of February. That's a random variable, capital X. You're sitting in your office in the beginning of the year. What is going to be your forecast? It's going to be the expected value of the random variable x. So this is the forecast that you make at this point in time. Now time goes by and we are sitting now in the beginning of February or the end of January. At that time, you obtain some new information, which is the value little y of a random variable capital Y. What should your new forecast be? Well, once you have this information in your hands, your new forecast should be the expected value of x given the specific available information that you have. So this is the revised forecast as calculated at the end of January. But if you're sitting here in the beginning of the year and you ask yourself, what is the revised forecast going to be? Your answer will be, I don't know what it's going to be. It's random. It depends on what capital Y will end up being. My revised forecast is a random variable, the expected value of x given y, which will take this particular numerical value if it turns out that the random variable y takes a specific value little y. So this is the forecast calculated at this point in time. This is the forecast viewed in the beginning of the year, at which time we do not know yet the value of the revised forecast. Now, what does the law of iterated expectations tell us in this case? It tells us that the expected value of the revised forecast is the same as the original forecast. What does this mean in practical terms? It means that given today's forecast, the original forecast, you do not expect the next forecast, the revised one, to be higher or lower. It could be either higher or lower, but on the average, you expect the revision of the forecast going from this one to that one, the revised one, that revision on the average to be equal to 0. You do not expect forecasts to be revised either upwards or downwards on the average. Of course, this is not what happens always in real life. So suppose that capital X, the quantity you're forecasting, is the cost of some big project. And your original budget or original forecast, expected value of X, is what you expect the cost of the project to be. Well, from experience with real life, we kind of know that budgets or cost estimates tend to be revised upwards more often than downwards. Does this real life fact contradict the law of iterated expectations? Well, not really. What is going on here is that real life forecasts are not really honestly calculated expected values, but maybe they're calculated with some implicit or hidden biases so that the forecasts that are given are actually not the expected values. So there is no contradiction between this mathematical fact and possible life experiences. We have defined the conditional expectation of a random variable given another as an abstract object which is itself a random variable. Let us now do something analogous with the notion of a conditional variance. Let us start with a definition of the variance, which is the following. We look at the deviation of the random variable from its mean, square it, and take the average of that quantity. If we live in a conditional universe where we are told the value of some other random variable capital Y, then inside that conditional universe, the variance becomes the following. It is defined the same way. Well, in the conditional universe, this is the expected value of x. So this quantity here is the deviation of x from its expected value in that conditional universe. we square this quantity, we find the square deviation, and we look at the expected value of that square deviation. But because we live in a conditional universe, of course, this expectation has to be a conditional one given the information that we have available. So this is nothing but the ordinary variance, but it's the variance of the conditional distribution of the random variable capital X. This is an equality between numbers. If I tell you the value of little y, the conditional variance is defined by this particular quantity, which is a number. Now, we proceed in the same way as we proceeded for the case where we defined the conditional expectation as a random variable. Namely, we think of this quantity as a function of little y, and that function can be now used to define a random variable. And that random variable, which we denote this way, this is the random variable which takes this specific value when capital Y happens to be equal to little y. Once we know the value of capital Y, then this quantity takes a specific value. But before we know the value of capital Y, then this quantity is not known, it's random, it's a random variable. Let us look at an example to make this more concrete. Suppose that y is a random variable, we draw that random variable, and we're told that conditioned on the value of that random variable, x is going to be uniform on this particular interval from 0 to y. So if I tell you that capital Y takes on a specific numerical value, then the random variable x is uniform on the interval from 0 to little y. A random variable that's uniform on an interval of length little y has a variance that we know what it is. It's y squared over 12. So this is an equality between numbers. For any specific value of little y, this is the numerical value of the conditional variance. Let us now change this equality between numbers into an abstract equality between random variables. The random variable variance of x given y is a random variable that takes this value whenever capital Y is little y, but that's the same as this random variable. This is a random variable that takes this value whenever capital Y happens to be equal to little y. So we have defined the abstract concept of a conditional variance, similar to the case of conditional expectations. For conditional expectations, we had the law of iterated expectations that tells us that the expected value of the conditional expectation is the unconditional expectation. Is it true that the expected value of the conditional variance is going to be the same as the unconditional variance? Unfortunately, no. Things are a little more complicated. The unconditional variance is equal to the expected value of the conditional variance, but there is an extra term that is the variance of the conditional expectations. The entries here in red are all random variables, so the conditional variance has been defined as a random variable, so it has an expectation of its own. The conditional expectation, as we have already discussed, is also a random variable, so it has a variance of its own. And by adding those terms, we get the total variance of the random variable x. So what we will do next will be first to prove this equality and then give a number of examples that are going to give us some intuition about what these terms mean and why this equality makes sense. We will now go through a derivation of the law of total variance. This particular derivation is not insightful. It will not really give you any intuition as to why the law of total variance is correct. On the other hand, it involves some interesting manipulations that will be useful to be able to follow and understand the kinds of objects that are being moved around and why each step is valid. Our derivation relies on the standard formula that we have on how to calculate variances. And our first step is to apply this formula to the conditional variance. Now, the conditional variance is like an ordinary variance, except that it is calculated in a conditional universe. So we apply this formula, except that the expectation of x squared is the expectation calculated in the conditional universe, and similarly for the next term it's the square of the expected value of x, but it's the expected value of x as calculated in a conditional universe. So this is an equality between numbers. What does it translate to? This has been defined as a random variable that takes this value when capital Y is equal to little y. What is the random variable that takes this value when capital Y is little y? Well, this random variable here is a random variable that takes this value when capital Y is equal to little y, and this random variable here is a random variable that takes this numerical value when capital Y is equal to little y. So, to summarize, this is a random variable that takes this numerical value when capital Y is equal to little y, and this is a random variable that takes this value when capital Y is equal to little y. This expression, the left-hand side, is equal to the right-hand side for all y's, and therefore this random variable and that random variable always take the same numerical values no matter what y happens to be. So these are identical random variables, and so we have this equality between random variables. The next step, as we're working towards calculating this first term here in the law of total variance, is to take the expectation of this expression. What is it? We take the expectation of the first term. It's the expectation of a conditional expectation, and according to the law of iterated expectations, it is the same as the unconditional expectation. And then we have the expected value of the next term. Next, we want to make some progress towards calculating this second quantity in the law of total variance. And the way to calculate it is to just apply this general property of variances to the special case where x gets replaced by the expected value of x given y. So the first term will be the expected value of our random variable squared. Our random variable is the expected value of x given y. And the second term involves the expected value of the random variable whose variance we're considering. So it's the expected value of this random variable. So it's the expected value of the conditional expectation. And everything gets squared. What is this term? By the law of iterated expectations, the expected value of a conditional expectation is the same as the unconditional expectation. So this last term here is of this form. What we will do next is to take this expression here and that expression here and add them together. When we add them, we notice that this term and that term are the same, so they cancel out, and we're left with the expected value of x squared minus the square of the expected value. But we know that this is the same as the variance of x. So we have proved that the sum of these two terms, which are the two terms up here, give us the variance of x. We will now go through an example which is essentially a drill to consolidate our understanding of the conditional expectation and the conditional variance. Consider a random variable x which is continuous and is described by a PDF of this form. Whenever we have a PDF that seems to consist of different pieces, it's always useful to divide and conquer. And the way we will do that will be to consider two different scenarios that x falls in this range. And in that scenario, we say that a certain random variable y is equal to 1, and another scenario in which x falls in this range, and in that case, we say that y is equal to 2. Let us now look at the conditional expectation of x given y. What is it? Well, it is a random variable. which can take different values depending on what y is. If y happens to take a value of 1, then we are in this range, and the conditional PDF of x, given that y falls in this range, keeps the same shape, it's uniform, and so its mean is going to be equal to the midpoint of this interval, which is 1/2. And this is something that happens when y is equal to 1. What is the probability of this happening? The probability that y is equal to 1 is the area under the PDF in this range. And since the height of the PDF is 1/2, this probability is 1/2. The alternative scenario is that y happens to take the value of 2, in which case x lives in this interval. Given that x has fallen in this interval, the conditional expectation of x is the midpoint of this interval, and the midpoint of this interval is at 2. And this is an event that again happens with probability 1/2 because the area under the PDF in this region is equal to 1/2. So the conditional expectation is a random variable that takes these values with these probabilities. Since we now have a complete probabilistic description of this random variable, we are able to calculate the expectation of this random variable. What is it? With probability 1/2, the random variable takes the value of 1/2, and with probability 1/2, it takes a value of 2, and so the expected value of the conditional expectation is 5/4. But the law of iterated expectations tells us that this quantity is also the same as the expected value of x. So we have managed to find the expected value of x by the divide and conquer method by considering different cases. Let us now turn to the conditional variance of x given y. Once more, this quantity is a random variable. The value of that quantity depends on what y turns out to be. And we have again the same two possibilities. Y could be equal to 1 or y could be equal to 2. And these possibilities happen with equal probabilities. If y is equal to 1, conditional on that event, x has a uniform PDF on this range on an interval of length 1, and we know that the variance of a uniform PDF on an interval of length 1 is 1/12. If, on the other hand, y takes a value of 2, then x is a uniform random variable on an interval of length 2, and the variance in this case is 2 squared, where this 2 stands for the length of the interval, divided by 12, which is the same as 4/12. So we now have a complete probabilistic description of the conditional variance as a random variable. It's a random variable that with these probabilities takes these two particular values. Since we know the distribution of this random variable, we can certainly calculate its expected value. And the expected value is found as follows. With probability 1/2, the random variable of interest takes a value of 1/12. And with probability 1/2, this random variable takes a value of 4/12. And this number happens to be 5/24. Finally, let us calculate the variance of the conditional expectation. Since we have complete information about the distribution of the conditional expectation, calculating its variance is not going to be difficult. So what is it? With probability 1/2, the conditional expectation takes a value of 1/2. We subtract from this the mean of the conditional expectation, which is 5/4, and we take the square of that. So this term is the square of the deviation of the value of the random variable of 1/2 from the mean of that random variable. And we get a similar term if y happens to be equal to 2, with probability 1/2, our random variable takes a value of 2, which is so much away from the mean of the random variable, and then we square that quantity. If we carry out the algebra, the answer turns out to be 9/16. And now we can go back to the law of the total variance and calculate that the total variance is equal to the expected value of the variance, which is 5 over 24. And then we have the variance of the expected value, which is 9 over 16. And this number evaluates to 37 over 48. So we have managed to find the variance of this random variable using the divide and conquer method and the law of the total variance. We will now go through another example to consolidate our intuition about the content of the law of iterated expectations and the law of the total variance. The example is as follows. We have a class, and that class consists of 30 students in total who are divided in two sections, the first and the second section. Let xi be the score of student I, let's say the final grade in the class. We consider the following probabilistic experiment. We pick a student at random, uniformly, so that each student is equally likely to be picked, and we define two random variables. X is a numerical random variable that gives us the score of the selected student. So if student I is selected, the value of the random variable capital X is xi. And capital Y is defined as the random variable, which is the section of the selected student, so that Y takes values 1 or 2. We're given some information. For the first section, the average of the student scores is 90. For the second section, the average of the student scores is 60. Given that information, what is the expected value of the student score? Well, each student is equally likely to be picked, so has probability 1 over 30 to be picked, and this multiplies the score of the student. So this is the expected value of the random variable of interest. What is this number? Well, we need to calculate the sum of the xi's. The sum of the first 10 xi's is equal to 90 times 10. And the sum of the xi's in the other section is equal to 60 times 20. And we carry out the calculation and we find that the answer is 70. Now let us look at conditional expectations. If y is equal to 1, this means that a student from section 1 was picked. And within that section, each student is equally likely to be picked. So the outcome of this random variable is equally likely to be any one of these xi's. Each xi gets picked with probability 1 over 10. And so the expected value of this random variable is 90. Similarly, for the second section, the expected value of the score of a randomly selected student, given that the student belongs in that section, is equal to 60. With this information available, now we can describe the abstract conditional expectation, which is a random variable. This random variable takes the value of 90 if a student from the first section was picked, and the value of 60 if a student from the second section was picked. What is the probability of this event, that a student from the first section was picked? Given that the first section has 10 out of a total of 30 students, this probability is 1/3, and therefore this probability is 2/3. Now that we have the distribution of this random variable, we can calculate the expected value of this random variable, which is 1/3 times 90 plus 2/3 times 60. And this number evaluates to 70, which, of course, it's no coincidence, is the same as the average over the entire class. By the law of iterated expectations, we know that this quantity should be the same as this quantity. So the law of iterated expectations allows us to calculate the overall average in the entire class by taking the section averages and weigh them according to the sizes of the different sections. It's a divide and conquer method, and it is similar to what we have been doing when we use the total expectation theorem to divide and conquer. We continue with our example, and here is a summary of what we found so far. The conditional expectation is a random variable that takes these two values with certain probabilities, and the mean of this random variable is equal to 70. Let us now calculate the variance of this random variable. This random variable with probability 1/3 takes a value of 90, which is this much away from the mean of this random variable, which we square, and with probability 2/3 it takes a value of 60, which is this much away from the mean of the random variable. We square this as well, and when we carry out the calculation we find that this number is equal to 200. Let us now continue and suppose that somebody gave us this piece of information. For the first section, this is the deviation of the ith student from the mean of that section. So this is the sum of the squares of the deviations, and then we average over all the students. We will use these data to calculate certain quantities. For example, the variance of the scores in the first section. Now, in the first section, with probability 1/10, we pick the ith student that has this score, and this is the deviation of that student from the mean of that section. So this is the same as the mean squared deviation from the mean of the section, and this is exactly the variance within that section. It is the variance of the random variable, which is the score of a random student, given that we are selecting a student from the first section. For the second section, the story is similar. We're given this information, and this tells us the variance of the student scores within the second section. So now we can describe the abstract conditional variance. It is a random variable that takes this value with probability equal to the probability of selecting someone from this section, which is 1/3, or it takes a value of 20, which is the variance in the second section, and the second section is selected with probability 2/3. With this information at hand, now we can calculate the expected value of this random variable, which is 1/3 times 10 plus 2/3 times 20, which is 50/3. At this point, we have the two quantities that are necessary to apply the law of total variance. According to the law of total variance, the variance of the student scores throughout the entire class is equal to this number, which is 50/3, plus this number, which is 200. And this is the overall variance. Now let us interpret the law of total variance in this context. The interpretation is as follows. The variance of the student scores in the entire class consists of two pieces. The first piece looks at the variance inside each section, which is 10 or 20 depending on which section we're looking at, and we take the average over the different sections. So we look at the variability of the scores within a typical section, and then we average over all the sections. The other term looks at the means in the different sections and figures out how different are these means. How much do they vary from the overall class average? It measures the variability between different sections. So the overall randomness in the test scores can be broken down into two pieces of randomness. One source of randomness is that the different sections have different means. The other source of randomness is that inside each section, the students are different from the means of their section. And these two pieces of randomness together add up to the total randomness of the student scores as measured by the variance of the entire class. We now study a model that involves the sum of independent random variables, but with a twist. it's going to be the sum of a random number of independent random variables as opposed to a fixed number. This is a model that shows up in a variety of applications, but it will also help us fine-tune our command of the law of iterated expectations and the law of total variance. The story goes as follows. You go shopping and you visit a number of stores, except that the number of stores that you will visit is itself a random variable. At each one of the stores, you spend a certain amount of money, we denote it by xi. And we make the assumption that the xi's are drawn from a certain distribution, they're identically distributed, and they're independent of each other. We also make the assumption that the xi's are independent of capital N. This means that no matter how many stores you visit, the xi, the amount of money you spend in each one of the stores that you visit, is a random variable that's drawn from a common distribution which does not change no matter what capital N is. With these assumptions in place, let us now focus on the total amount of money that you are spending. This is the sum of random variables, but with the extra twist that the index goes up to capital N, which is itself a random variable. How do we deal with this situation? One approach that's always worth trying when faced with a complicated problem is to try to condition on some information that will make the problem easier. In this case, we can condition on the value of capital N taking a fixed specific value, because in that case we will be dealing with the sum of a finite number of random variables where that number is a fixed specific number. And this is a situation we have encountered before and know how to deal with it. So let us get started. Let us calculate the expected value of y if we condition on the number of stores. Let's say, for example, someone tells us that we visited 5 stores. Then the expected value of y is going to be the expected value of the sum of the amount of money you spend in each one of those 5 stores. In our instance, it's that random variable capital N. But since I told you that capital N takes a specific numerical value, this means that this instance of capital N in the index of the summation can be replaced by little n. If I tell you that capital N is equal to little n, then this number here, capital N, becomes the same as little n. Here we use now the assumption that capital N is independent from the xi's. Here we have the sum of a fixed number of random variables. All of them are independent of capital N. If I give you some information on capital N, this does not change the distribution of the xi's, so the conditioning does not affect the answer. The conditional expectation is going to be the same as the unconditional expectation. And now we have the expected value of a sum of random variables. Each one of them has a common expectation. Let's denote it with this notation. This is the common expected value of all the xi's, and we're adding n of them, so we obtain n times this expectation. Now let us apply the total expectation theorem. We take the familiar form of the total expectation theorem, and in here we can plug in the expression that we have just found, which is n times expected value of x. Now the expected value of x is just a number, and then we have this summation here, which we recognize to be just the definition of the expected value of n. And so we come to the conclusion that the expected amount of money that you will be spending is equal to the following product: the expected number of stores that you visit times the expected amount of money that you will be spending at each store. This is a quite plausible answer. It makes sense. On the average, the amount of money you spend is equal to the average number of stores times the average amount of money in each store. So it is intuitively what you might expect. On the other hand, we know that reasoning on the average does not always give us the right answers, so it's important to corroborate this particular formula by working out a mathematical derivation. Now let us carry out a second mathematical derivation using the law of iterated expectations. To use the law of iterated expectations, we need to put our hands on this random variable, the abstract conditional expectation. What is this object? It's a random variable that takes this value whenever capital N is equal to little n. So it's an object that takes this value whenever capital N is equal to little n, but that object is the same as this random variable, because this is the random variable that takes the value here when capital N is equal to little n. Therefore, the abstract conditional expectation takes this particular form here, which we can substitute inside this expectation here. And now, notice that the expected value of x is a constant, so it can be pulled outside this expectation, and we're left with the product of the expected value of n times the expected value of x. So this completes the derivation of the expected value of the sum of a random number of random variables. We now continue the study of the sum of a random number of independent random variables. We already figured out what is the expected value of this sum, and we found a fairly simple answer. When it comes to the variance, however, it's pretty hard to guess what the answer will be, and it turns out that the answer is not as simple. So this is what we will try to calculate now. The way to proceed will be to use the law of total variance, which effectively breaks down the problem by conditioning on the value of the random variable capital N. So let us start. We have already figured out that if I tell you the value of capital N, then the expected value of the random variable y is just this number capital N, the number of stores you are visiting, times how much you are spending in each one of the stores. Using this information, we can now calculate this term, the variance of the conditional expectation. What is it? It's the variance of capital N times the expected value of x. Now the expected value of x is a constant, and when we multiply a random variable with a constant, what that does to the variance is it multiplies the variance with the square of that constant. And this gives us this term in the law of total variance. Let us now work towards the second term. If I tell you the number of stores, then the random variable y is just a sum of a given number of random variables. And as we discussed before, the conditioning that we have here may be eliminated because these random variables are now independent of this random variable capital N. Their distribution does not change based on this information, and so we obtain the unconditional variance. Now the unconditional variance of a sum of n random variables is just n times the variance of each one of them, which we denote with this notation. Now let us take this equality, which is an equality between numbers, and it's true for any particular choice of little n, and turn it into an equality between random variables. This is the random variable that takes this specific value when capital N is equal to little n. So this is a random variable that takes this specific value when capital N is equal to little n, but this is also the same as this random variable, n times the variance of x, because this random variable takes this particular numerical value when capital N is equal to little n. Now that we have an expression for the conditional variance as a random variable, we can take the next step and calculate the expected value of the conditional variance. The expected value of the conditional variance is simply the expected value of this expression that we calculated up here. And now the variance of x is a constant and can be pulled outside the expectation, which leaves us with this expression here. Now that we have calculated both terms that go into the law of total variance, we can add these two terms. We have one contribution from here, this is this term, and another contribution from here, which is this term. What this expression tells us is that the variance of the total amount that you spend, which is a certain measure of the amount of randomness in how much you're spending overall, this amount of randomness is due to two causes. One cause is the randomness that there is in how much money you spend in any given store, and that's captured by the variance of x. It's the variance of the distribution of the amount of money that you spend in a typical store. But there is another source of randomness, and that source of randomness comes from the fact that the number of stores itself is random, and this gives us this contribution to the variance of y. By taking into account these two sources of randomness, we can figure out the overall variance of the random variable y. As you can see, this is a formula that would be hard to guess by just reasoning intuitively. And so it's a demonstration of the power of the law of the total variance.